So let's start with a review of some stuff that we do know already. Okay, so we know that if the curl of a vector field is 0, this is the same as it being conservative. Okay, so this means that this is the same as f is equal to the gradient of some potential function. That is the equivalent of saying that the integral over some curve of f dot dr is equal to p of b minus p of a, and does not depend on the path. Okay, we also have that if we do a closed loop, so if we do a loop that goes all the way around, we have that this is the same as f dot dr. This is just going to be 0 because there's really no boundary, or if we pick one point we go all the way around, so pb is the same as pa, and we subtract the same thing and we get 0. Okay. And then we also have Green's theorem. Is that what I want to use? Yeah. It says that the integral over some surface of f dot ds is equal to no, sorry, I don't need that right now. Okay, so this kind of vector field, they call it irrotational. Okay, because this curl of f usually stands for like kind of some sort of, or usually represents some sort of rotation or angular velocity or something like that. Okay, that's what this curl usually represents. Something like, kind of rotation. All right, we also have another type of vector field. We have if the divergence of f is 0. Okay, and I know I've kind of skipped over what this del cross f means and this del dot f means, but I can review that a little bit later if you guys need. Okay, so here's just some stuff that's useful to know, but it kind of helps put things in context. So this is an irrotational field. This one, they call it solenoidal. I think that's how you spell it. Maybe it's an E. Solenoidal. But the thing to know is that f is equal to the curl of some function. So this one I know you guys didn't talk about, but this is called the vector potential here. But let's just see how it relates to these other ones. So here, what we have is that the integral over the surface of, integral over the surface of f dot ds is equal to what? It's equal to, so this is Stokes' theorem. Let's see, how do I want to write this? I will write it like this. A dot dr over c. So c is the boundary of this S. Let me say does not depend on the path, the surface. Okay, it only depends on the boundary C of that surface. And what if there is no boundary? So if this is a closed surface, so for example, a closed surface would be something like a sphere, right, where there's no that is a terrible sphere. But basically where there's no like edge to it. So if I'm walking around a sphere, I'm never gonna walk off of the sphere. Whereas if I did maybe like a half sphere, the boundary of the sphere would be the circle right here around the edge. Okay, basically if there's no way for me to get from the inside to the outside or the other way around. Okay, so if I have something like this, and I'm integrating around a surface, then this is going to be 0. Because there's no boundary, right? And it doesn't depend on the surface, it only depends on the boundary, and if there's no boundary, it's going to be 0. So this right here is Stokes' theorem. So I hope you guys can see kind of some of the parallels. Where Stokes' theorem is just kind of like the next dimension up version of this fundamental theorem for line integrals. Okay, and then we also have, actually that divergence theorem is a little bit different. Okay, any questions on that? So we have these two types of vector fields. We have an irrotational vector field and a solenoidal vector field. And so not every vector field is one of those. But it turns out, this is just interesting to know, that every vector field is a combination of a irrotational vector field and a solenoidal vector field. So this is equal to the gradient of something plus the curl of something else. So every vector field you can write this way, no matter what. So that's not gonna come up for us at all. But so let's go ahead and have a look at Stokes' theorem. And let me rewrite Stokes' theorem one more time in the way you're more familiar with. So Stokes' theorem says that the integral over a surface of the curl of something, I'm going to use A dot ds is equal to the line integral over the boundary of A dot dr. Okay, so that's what I'm going to be using. That's what I'm going to be using in these next couple examples. Okay, so use Stokes' theorem to evaluate the integral of the curl of f. So it's going to be taking this and turning it into a line integral. Sometimes it might be easier if you want to go the other way around. If you take, I think that's kind of rare though, but if you take a line integral, you can turn it into a surface integral. But generally this is what you want to do. Take a surface integral, turn it into a line integral. That's a lot easier to evaluate. So the first thing I need to do is to parameterize, no, I don't need to parameterize my surface. I'm doing a line integral. Okay, so what is the boundary of this surface? Then what is the boundary of the surface? Well, it says it's the hemisphere, x squared plus y squared plus z squared equals 9 with z bigger than or equal to 0. So that means my surface is kind of like the top half of a sphere. Okay, it's the top half of a sphere. So the boundary is just going to be when z equals 0, this bit right here. So the boundary, my contour, is going to be when z equals 0, so that's going to be x squared plus y squared equals 9. So now I'm going to use Stokes' theorem to say that this is equal to the integral over c of f dot dr. So I need to parameterize this. I'll do that in terms of polar coordinates. So I will do x equals r, well, yeah, equals 3 cosine t, y equals 3 sine t. So I have r of t is equal to xy, right? So this is going to be 3 cosine t, 3 sine t, and 0, right? The z component is 0. So I'm trying to evaluate this line integral of f dot dr. So just like any other line integral, this is going to be f dot r prime dt. So r prime is derivative of cosine is negative sine. Derivative of sine is cosine. That's 0. And I need to figure out what is f in terms of r. So f of r of t is, so we have, well, cosine of 0 is 1, and we have y, so it's going to be 6, sorry, y is sine, yeah, so 6 sine t. Sine of 0 is 0, so the j component is going to be 0. And then we have 3 cosine t e to the 3 sine t. Okay, that might look like it's going to give us trouble, but it's actually going to cancel out. So when I do this dot product, and we're going to integrate from t going from 0 all the way around to 2 pi. So f dot r prime, so that's f dot r prime, I'll just kind of do that here. So we have minus 18 sine squared t plus 0, right? That times that is 0, plus 0, that times that is 0, dt. So that's minus 18 integral from 0 to 2 pi of, I can rewrite this as 1 minus cosine of 2t over 2 dt. And I integrate to get t integral of cosine is sine from 0 to 2 pi. Okay, so when I plug in 2 pi and 0 to either to sine term, that goes away. The 0 doesn't contribute anything, so all I'm going to have is minus 18 pi. Okay, so that was a way that I was able to take this surface integral, right? Because if you remember from last week, computing these surface integrals is not fun. It's a lot of work. Now this wasn't like super easy either, but it's a lot easier than having to parameterize the surface, do the derivatives, do the cross product, do the norm, all of that stuff. So it's a lot easier to actually just parameterize the curve than having to parameterize the whole surface. Any questions from this example? Yeah, that's all I need to do. I just need to parameterize the line, and I don't care what the actual shape of the surface is. I just need to find what is the edge of that surface. That's really the whole point of this, is that I don't care what the surface is. I just care what the line is, the edge. Okay. What is equation 3? I might have to look that hint up. We'll see. Okay, so here, the shape is basically the same, except now it's kind of, I should have done this differently. Go this way. Whatever. So it's supposed to be the top half, or the like right half of a sphere. So it's supposed to be just the part with the positive x-axis. So I still cannot draw today. Basically, the boundary is going to look something like this, where it goes through the z and the y-axis, but x is 0. Right, because the surface is on the positive x-axis, so the edge of that is going to be when x equals 0. So the contour that we're interested in, the curve that we're interested in, is when x equals 0. So that means that y squared plus z squared equals 1. Okay, and then we can parameterize this the same way. Y equals 1, just cosine t, z equals sine t. So our r is going to be 0 cosine t sine t. I'm going to need r prime, so I do 0 minus sine cosine. Okay, and then I need to rewrite f in terms of r of t. Okay, so this is e to the 0 cosine of z. Let's see, what is this hint that it gives? Use equation 3. Let's see. It says, okay, so the way I have this written is that this would be e to the 0, 0, cosine of cosine of t. I don't think that's going to be right. Or I don't think that's how we're going to want to do this. This is going to be 0, and this is going to be 0. Oh, wait, no, this works out fine. Should it be sine? It probably should, yes. Okay, it's going to work out, though. It's going to be 0, or x1 is 0. 0 times 0. Okay. So now what the question is actually asking the same part from up here. So you use Stokes theorem to evaluate this flux integral. So what it's asking is use Stokes theorem to evaluate this. And let's see. So Kevin, it's not going to make a difference, and you'll see why once I do this. So this is the integral over the boundary of f dot dr, which is the integral over the boundary of f dot r prime dot or times dt. There's no dot there. Together. Okay, so here that's just going to be 1, so I can erase that. And I do f dot r prime, and what do we get? What we end up with actually is just 0. Is just 0. So what that means actually is that this right here, I probably could have written it as the gradient of some function. I wouldn't really want to try to figure that out, but it means that this is the gradient of some function. Because no, I'm sorry, that's not right. That's not right. It means that the divergence is 0. I'm not sure. Okay. Anyways, that's the result. And it was nice because most things canceled out. So are we clear on Stokes theorem? This is Stokes theorem right here. It lets us turn the flux integral of a curl into a much easier line integral around the boundary of the curve. No, I'm about to do that next. So, if there's no more questions on Stokes' theorem, then I will go ahead and move on to divergence theorem. So the divergence theorem let's see. Let's put it this way. So here, if I have the integral of p dot dr from point A to point B, right? This is p evaluated from A to B. If I have the integral of the curl over a surface, this is equal to integral over the boundary. This is just Stokes' theorem. And for the divergence theorem, what this tells me, so the divergence gives me a scalar, so there's no dot product. This is just the integral over some closed region divergence of f dv. So this is going to be like dx dy dz. So there's nothing really like special about this region. It's just a triple integral, just like we were doing a couple sections ago. There's nothing special about how to compute this. This is going to be equal to the integral over the bound. Let's see, I don't want that. This is going to be equal to the integral over the surface of the flux of this. So notice how in each of these, right, I'm taking an operation, an integral, and kind of changing it into something kind of lower dimension. So here, instead of doing this integral, I'm just evaluating it on the endpoints, right, on the edges of my domain curve. Here, if I'm integrating over surface, I'm actually just integrating this over the boundary, the curve that's the boundary. Here, I can take this triple integral and just evaluate it on the boundary of the surface. Now, actually, usually we use this one kind of going the other way because this is usually a lot easier to integrate than this one. Because to do a surface integral, you have to parameterize a surface and all that other stuff.
Mic off. Mic on.
But here with the triple integral, we just set it up like any other triple integral and take the divergence. I had another point. What was it? Oh, yeah. So what does this actually represent? What does the divergence represent? So here, this flux integral, if we have some surface, okay, imagine this is a 2D thing. This flux integral over this surface kind of tells me maybe I have like water or something flowing. It's going to tell me how much is flowing out and how much is flowing in. Right, I'm adding this all up. Okay, so I'm looking at the integral of all of this. And so when I integrate this up, what it's telling me is, was there a net flow in or a net flow out? It's kind of, so how much came in or how much went out, something like that. And I can change that into the integral of the divergence. Okay, but that's why, so this right here, they call it the flux, right? So how much came in and how much went out, that's the flux. That's why they call this like a flux integral. It's how much is going past this boundary. Okay, so let's do an example. So these ones are actually pretty simple. We're going to be taking a surface integral, a flux integral, and changing it into um, a triple integral. Right, so it says use the divergence theorem to calculate the surface integral, blah, that is, calculate the flux of f across S. So again, we want to compute what is this. Well, that's just going to be the triple integral over the region contained by this surface, so we'll have to figure that out, of the divergence of f dv. So that's going to be like dx dy dz. So first, let's go ahead and just compute the divergence. So the divergence is the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. So it's kind of like the gradient, but it's more like a dot product with our vector function. Notice that it's always a scalar. So this is going to give you a scalar result. So this is going to give us e to the x sine y plus e to the x, those cancel out. The derivative cosine is negative sine, and derivative of this with respect to z is going to be plus 2yz. So those cancel out, and I just get that the divergence is just 2yz. So that's what I'm going to be integrating. Let's see what my surface is. Where S is the box bounded by the planes x equals 0, x equals 1, y equals 0, y equals 1, and z equals 0, and z equals 2. So this is fairly straightforward, right? If I was to have to do a surface integral, I'd have to integrate over each of these surfaces individually. So I'd have to parameterize each of these surfaces and integrate over each of those surfaces individually, right? So it's describing a box like this. So having to do a surface integral over something like this would be a real pain. But here, being able to use the divergence theorem,
Mic off. Mic on.
I can actually do this really simply. So this triple integral, what I'm integrating 2yz dz dy dx. It doesn't really matter which order I do them in, because z goes from 0 to 2, y goes from 0 to 1, and x goes from 0 to 1. So this is separable. So I can write this as 2 integral from 0 to 1 of y, integral from 0 to 2 z, integral 0 to 1 dx, which gives me integral of y, so that's 2 times y squared over 2, 0 to 1, z squared over 2 from 0 to 2, and then that's just going to be 1. And then actually evaluating, I get a half. So 2 times 1/2 times, that's 4 over 2, which is 2, times 1. End result is just 2. Okay, so the main part right here, I wanted to compute this flux integral over this whole surface. And I was able to change that into a volume integral that's a lot easier to set up. Okay, because I would much rather do this volume integral than have to parameterize that surface. Any questions? Okay. Um, so same sort of thing. It wants us to compute the flux over S. So instead, I'm going to use the divergence theorem and compute the triple integral over the region bounded by that surface of the divergence dv. And I'm probably going to have to use something like, what is this, cylindrical coordinates? Yeah, probably cylindrical coordinates. But first, let's compute the divergence. So this is going to be derivative of the x component with respect to x, so that's going to be 3x squared y plus derivative of the y component with respect to y is minus 2x squared y, and interesting, minus derivative of the z component with respect to z. So this is x squared y. Did I do that right? Because that means that this is 0, which would mean that the whole thing is just 0. Let me double check that. So I do so that becomes 3x squared times y, and then we have 2x squared times y minus x squared. Yeah, okay. So here the divergence was 0, so there's nothing to integrate. The rest of this is just extra to throw you off. But here the divergence is 0, so that means there's no net flux over this region. That's anticlimactic. Let me pull up another example. Um, let's see if this one's more interesting. Okay, let's try a different one. So again, just like before, it's asking for the flux integral. It's asking for the integral over the surface. It gives us the surface of f dot ds. I don't want to parameterize that surface, so instead I'm going to use the divergence theorem to integrate over that cylinder of the divergence dv. So first thing, I'm going to compute the divergence. This is going to be 3y squared plus 0 plus 3z squared. I see. Okay, so that's going to be 3 times y squared plus z squared. And the region we're integrating over is the cylinder y squared plus z squared equals 1, and x goes from -1 to 2. So this makes me think that I should do cylindrical coordinates. Okay, because I have like a cylinder and it kind of comes along the x-axis. Um, so I'm going to set x equal to x, y equal to, what's the radius? Radius is 1. Cosine, r cosine t, and z is going to be equal to r sine theta. So we have that x is between 2 and -1. r goes from 0 out to 1, and theta, oops, that should be, goes from 0 all the way around to 2 pi. So I want to integrate this. So this becomes the triple integral of 3 y squared plus z squared, that's going to be r squared, times r, oops, r, r dr d theta dx. This goes from 0 to 1, 0 to 2 pi, and then from -1 to 2. It's separable, so this becomes 3 integral r cubed from 0 to 1 dr, integral from 0 to 2 pi d theta, integral from -1 to 2 dx, which is just going to give me 3 times 1/4 times 2 pi times 3, which is, let's see, 9 times, let's see, those cancel, 9 pi over 2. Okay, let's see how much time I have left. All right, I'm just about out of time. Questions? I can do any other examples that you guys want. So the on the short review that was sent out, I tried working through the first question, and I spent a good 30 to 40 minutes trying to figure out how to do it, and I could not figure out how to get the integral at the very end. So if you're going to try that and you get stumped, don't worry about that. The second and third problems I posted the solutions to online. You guys should see a notification about that. So for the divergence theorem, the idea is that we don't want to parameterize the surface, so we shouldn't need to parameterize the surface. So here with you're talking about with the r and theta. What did I do the r and theta? So yeah, in general, I'll just say that doing this surface integral is going to be a lot more difficult than doing this volume integral. So very rarely do you want to actually compute the surface integral. Um, maybe if there's some nice symmetry, you can do that. But in general, this is going to be a lot harder to integrate than this. So most most often, you're going to have this flux integral, and even in applications, right? You're going to have this flux integral, and you're going to transform it into a triple integral. That's a lot easier to integrate. So like maybe if you had a very simple example of something like a square box, and we know that the vector field is completely like horizontal. In a case like this, we know that the integral over the sides and the top would be 0. So then you'd only have to integrate over 2 sides, and that might make it a little bit simpler, but in general, it's not going to be that simple. So it usually it's a lot easier to just integrate over the whole domain and do the integrate the divergence. This will be short. One interesting application of this is we can also use the divergence theorem to get a formula for integration by parts. So the divergence of, let's say, the product of two functions. Let's say we have f dot g. So these are vector, no. Sorry, if I have a scalar function, let's call it f, and a vector function. I need better letters. Scalar function and vector function. Okay, the divergence of this is going to be the gradient of phi dot f plus phi times the divergence of f. Now, I'm just saying that for Stokes, we don't multiply by r prime. Let me get back to that. So for this real quick, if I integrate both sides over some region, right, so I'm integrating over some domain. Here I can use the divergence theorem and say that this is equal to the integral over the surface of phi f dot ds. That's equal to the triple integral of grad phi dot f dv plus the triple integral of phi div f. So I can rewrite this, and we have that basically it's an integration by parts formula. dv is equal to the surface integral of phi dot ds minus the triple integral of phi div f. So this should look very similar to integration by parts, where you have integral of u prime v dx equals u v on the boundary from a to b minus integral of v prime u dx. So, you should be able to see a similarity where instead of here evaluating on the boundary, now we have an integral on the boundary. But there's a whole bunch of other product or integration by parts formulas that you can derive using these rules. I don't think we're going to need those, but they exist. Okay, so also for Stokes, we don't multiply by r prime. The r prime is there, it's just kind of hidden. Let's see, for Stokes, here we go. So for Stokes, right, this surface integral is equal to f dot dr. So f dot dr is f dot r prime dt. So I'm not quite sure what your question is. Kevin. Well, are you asking why do we do that, or are we not supposed to do that, or what's your question? I don't quite understand your question. Okay, I'm going to go ahead and cut off the recording then.